Hello everyone, welcome to our webinar titled Continuous Object-Based Change Detection System Monitoring Urbanization Across Canada. We are going to be back in just 1 minute. We're just going to do some final preparations here. And we'll be right back. All right. Welcome everyone to our webinar. I'll just switch on my camera so I can say hello to you all. This is Kevin from PCI Geomatics. Glad to have you with us. Today we will be presenting our webinar, Continuous Object-Based Change Detection System Monitoring Urbanization Across Canada. And joining me today is Jason Flatt. Jason, I'm not sure if you can turn your camera on. We're all working from home, as you can see. So we're in our homes. I'm in my office, and Jason's in his living room there. So great to be here with everyone. We've got a couple of other people standing by. These are actually the people who have led a lot of this work. Wolfgang Luck, who's one of our senior scientists, has been key to a lot of this technology that we've developed. He's available to answer questions. Well, we've got ways of messaging him, and also Guillaume Morin, who is responsible for customer engagement and is also a big advocate of using cloud processing and GXL processing for large data sets. And Guillaume's been a key part of this project as well, so he's available to answer questions. And also Mauro Scatosa, who's on our who's in the back end there. He's monitoring, making sure we answer questions and so on. And will scream at me if the session stops working for some reason. So Mauro, I'm counting on you. All right. So so the webinar is on now. The lines are all muted during the presentation. You can raise your hand. Maybe just as a little experiment here, if we can get everyone to raise their hands at the same time. That way we can get a sense of who's paying attention, who's here. You could just kind of raise and lower your hand in the question panel there. That will give us a sense as to how engaged you are and if you're ready to go and if you can see everything on the screen. So that's great. I see a number of you raising your hands. So thanks for doing that. So the session is being recorded, but that doesn't mean you should leave. As you can see, it's very interactive. I'm here in Ottawa, Canada. Jason is in Ottawa as well. Mauro, we're all working from home, but we're here to interact with you live through this session. One of the quick things we wanted to mention is the fact that we have this campaign right now. It is an unprecedented time with COVID-19, and several weeks ago, we basically put in place a program to allow you to access Geomatica for free while you work from home. So if you have not heard of this, you can head to our website and see how you can participate in this program. It's very simple. You can basically request a license. Our support team has been, literally, I see the requests go out every day, and there's quite a few that go out every day. So if you're a student and you're finishing up projects, or if you're a professor and you're trying to help out your students, or if you're a private company or government institution that needs to have access to Geomatica to do some of your work, and you're having difficulties doing that because of accessing resources back inside your organization, you can install Geomatica locally on your machine and get a license to do that. So I want to talk about this webinar kind of in broad terms and position it correctly for everyone. So I'm sure a lot of you who are on this webinar today are thinking about really the impacts that this whole crisis is having in terms of of course, in terms of our lives, and I hope everyone is staying safe and staying home, if I haven't said that already. But what I've found very interesting, and I'm sure some of you have found interesting as well, is some of those really impressive images that have been coming out from European Space Agency, mainly through the Sentinel-5P sensor, which is measuring nitrogen dioxide, which is a GHG, a greenhouse gas emission, emissions gas. And there's these stunning maps that are showing a real drop in those emissions because of the reduced industrial activity related to this shutdown, this kind of unprecedented worldwide shutdown that we're living through. And really what this webinar is about is leveraging that Earth observation technology to do similar things. Hopefully you come away from this webinar with a sense of the important role that we play in our industry in terms of really leveraging the power of Earth observation to understand the impacts that we're having on the land over time. And what you're seeing on the screen is basically an animation of current day. So you see the current land use, or sorry, the current satellite image in the background that's high resolution. And what's happening is the polygons are changing colors because we're actually traversing through 30 years of time to see when the conversion of the land has occurred from different land use classes. And we'll get into a little bit more detail as to why that's important for climate change. But I can summarize it as follows. Accounting for the budget in carbon, whether we're increasing or decreasing the emissions of carbon, and how that's contributing to climate change, there's an absolute relationship between the information that can be extracted from Earth observation imagery and the science that is used by people like Environment Canada, which you'll hear about in this webinar. So really, there's a lot of capability, a lot of good that we can do as an industry in the world with our technology, and that's hopefully what I impart on you, or what we impart on you in today's webinar. So before we go there, I just want to do a quick poll. So the first one, I just want to get a sense of people who are here, kind of what size data sets are you typically working with? So are you working with sort of smaller data sets, 0 to 50 on a monthly basis, 51 to 500? Are you working with 501 to 5,000, or is it 5,000 plus? So if you think about your monthly utilization of data, there's a lot of changes happening as it relates to how people are consuming data. And specifically, when you're looking at these temporal trends over 30-year spans, depending on how small or how big of a geography you're looking at and how deep the stack is that you're going to create, you're really going to get into some big data sets. And that's a great opportunity. And really what's needed for us to leverage that opportunity is to make that technology available. And there's great technology that's been developed. Obviously, we're working on some of it, but it's very encouraging to see a lot of technology coming to market to make this possible. So I'm just going to close that down in 3 seconds. It seems like a lot of you are participating, which is great. So I'm going to close that down. And I'll share out the results. So it looks like a lot of people working with smaller data sets on a monthly basis, and then it kind of goes up. So it is a big number on a monthly basis, but there you go. That's information for everyone to ponder. And I'm going to switch now to talking a little bit about what do we mean when we say temporal analysis. So I've given you a little bit of a picture in terms of what does that mean in terms of creating these deep temporal stacks. And if I sort of keep going here, just going to make sure everything is good. Worst case scenario is nobody can hear me, so I think everyone can hear me. Everything's fine. All right. So really, what are we talking about here? If we think about remote sensing and Earth observation, there's been a period of time where we were busy making background maps or base maps, and we're still doing that. And there's a lot of value in doing that. But really, there's been a switch, and the switch has kind of occurred for a few reasons. the data sets that are collected by data providers such as USGS and the European Space Agency are increasingly made available free and open. So that means that you can download imagery or you can access imagery through a cloud platform, and it's much easier to do that. So there's way less friction in terms of your ability to leverage Earth observation as a resource, because the licensing restrictions around selling and distributing that data are changing and have changed quite a bit for some key sensors. The other key thing is just the compute infrastructure has caught up. So, maybe 10 years ago, if we talked about cloud and Earth observation, people kind of looked at us and said, that's not really logical because data sets are so big. But I'm sure you've all seen companies like Digital Globe and Airbus basically, order the Glacier service where they've had the trucks pull up and they load up all their data and they transport it physically to the online storage warehouses that Amazon makes available. And that then makes it possible to not only distribute that data openly in the case of USGS and ESA, but also to make it ubiquitously available through cloud distribution. And really there's some other trends that have made this possible, but those are the two that come to mind. But if we want to talk about switching from making base maps to measuring information off satellite imagery, we need to make the data so that we can actually perform quantitative measurements over time. And that really boils down to two things. And it's about reducing the noise in the data. Inherently, this Earth observation data is noisy, and we can remove that noise or eliminate or reduce the noise, mainly as it relates to two things. One is the radiometry. So if you think about atmospheric disturbances or clouds or cloud shadow, that's going to affect the radiometric measurement. And the other key thing is the geometry. So depending on how the data is corrected, what DEM is used, what level of precision was achieved at different times for the different data sets, then you might end up with issues related to geometry that are creating noise in the temporal data set that have to be accounted for and removed if we're going to really get down to a quantitative measurement. And so the next thing I want to sort of talk about is, if we put these things together, if we look at key requirements as it relates to time series analysis, we see this sort of breaking down into three pillars. And we'll walk you through the three pillars. The first one is what's known as analysis ready data. I'm going to go there next, and that kind of boils down to whatever I already talked about: super registration, radiometric normalization. The next one is having an environment that permits scaling of the data, and that's the open data cube, which we'll talk about later. And then the third piece is, once you have the data corrected, once you have it in an environment that you can explore it and have it easily available, then what you can do is you can perform multi-temporal analysis through the data cube to the analysis ready data. So what's ARD? Let's just get into this into a little bit more detail. So analysis ready data is basically a term, so I'll just read out the definition, a term used for Earth observation data that achieves rigorous scientific standards for measurements that are comparable through space and time. So everything I've been talking about is really what analysis ready data is about. It's a movement towards normalizing the data to make it so that you can make quantitative measurements. That's what analysis ready data is all about. Here we see one of the reasons ARD matters. This is a data set that I downloaded off USGS. It's a Sentinel-2 temporal data set over California. And what you're seeing is the raw data as it came from USGS. And you can see there's a little bit of moving around, right? There's pixel, 1 or 2 pixels, maybe more, like 3 or 4 pixel shift on some of those acquisitions. And that's because each time those images were created, they were orthorectified, using a particular approach, if you will. But when you go to stack them and try to drill through those archives, you end up with these issues with things kind of shifting around. If I show you what that looks like, when we apply our technology, so this is our super registration technology that's been applied to that exact same data set. It's very easy for me to do this. I've just used our GXL technology, which Jason's going to be showing you in a minute. And it brings all of that data down to a very, very accurate registration level so that you can compare over time and not have those geometric effects appearing in your data. The other key thing is the radiometry. So I talked about the noise in the geometry and the noise in the radiometry. So here, if we look at this particular field, we have two images collected about 4 months apart. So we have an image in July, which is in the summertime in Canada. We have a green field, and then an image in September. So the field has been harvested and is brown, appearing brown in the color, natural color view. And if we actually do a change detection on these two images, but if we do the change detection using data that hasn't been accounted for radiometry and one that has been accounted for radiometry, you can really see the difference. So on the left, you can see that our change detection is saying that there's been no change. It's low probability. It's in the 30th percentile, which is actually false because we know that that field went from green to fallow, and so it had a very high degree of change. So if we look on the right-hand side, what we see is basically that same change analysis that's been done, but it's been done this time on the radiometrically normalized data. So you can see that, this very simple case with just two images, you start to add that up over a large data set, and it really starts to throw errors into your analysis. So it's all about controlling the error bars, narrowing the errors, narrowing the noise, and getting to that quantitative measurement. That's really, really what this is all about. This is our workflow that we use to create that first pillar, that ARD. So to create that analysis ready data, what we've been busy doing, PCI, is we've been creating technology to allow our customers to create these deep temporal stacks. And here you have a schematic workflow that talks about some of the different technology that's either mandatory or optional. Jason's going to show you some parts of this workflow in GXL in a minute when we get to the demo. But really, we kind of start at the top with raw data, which is typically provided from a data provider, level 1 data typically. Then we would ingest that data, collect ground control points so that we can, orthorectify with respect to a reference image. You can see the reference image in orange. And then we can go through orthorectification. Now, the unique part of this workflow is after you get to orthorectification, you can see the super registration step. So what we can do is we can orthorectify all of the images, and then we can super register them all to the same reference image or to a middle image and kind of work our way up and down the stack. There's kind of different techniques so that we can get that geometry really taken care of. Then the next part relates to the radiometric normalization. So we have created technology to pull composites from Modus. There's a data product available from Modus that allows us to do radiometric calibration using as close as possible time-based composite to the acquisition dates. So we can do the spectral normalization with Modus. Then we can go one step further. There's an optional step there, which is called MRI Fusion. So this is a new pan sharpening technique that we have developed, which will allow you to bring some of the other spectral bands available from Sentinel-2 or other sensors, including Landsat. So you can actually do 10-meter analysis-ready data products from Sentinel-2, which is not something that's currently available. Only the 20-meter products are available through ESA. So you could actually generate 10-meter ARD products using our system. You could do the same thing with USGS. You could pull the 15-meter, you could pull the multispectral down to 15-meter with Landsat. And also you can apply this technology to other sensors like SPOT or RapidEye, other types of sensors that are out there that are maybe not as readily available in an ARD format. So you end up with an NBAR product, and then once you go through this production chain, which again, Jason's going to show you, you can export that out to the Open Data Queue. This is just kind of showing you super registration, what that's about. So we can achieve typically down to 1/10 of a pixel, and that's really going to remove the noise for the multi-temporal analysis. And then the radiometric pre-processing is, as I mentioned, using Modus library to perform that BRDF correction and to get to that nadir bidirectional reflectance distribution function, or NBAR product, which is really going to allow you to compare and get those quantitative measurements over time. This is again just showing the same results. I won't show that slide again. One of the other things that I mentioned quickly is MRI Fusion. So this is our pan sharpening technique that has actually been adapted for scientific use. So MRA is basically trying to retain the spectral fidelity while giving you that higher resolution product. So that if you're looking to detect changes over your time stack with more detail, you can go get that higher resolution, and you can also bring that spectral content down at the higher resolution. And this is some of the work that Wolfgang has presented at conferences over the last few years. And what's being shown here is the comparison of the changes, basically. So in the middle, we have our sort of our classical pan sharpening method, which is really more about creating an aesthetically pleasing image, which could be, you know, more suitable for things like making base maps. And you can see that you know, when we apply that algorithm, we actually have quite a bit of change in terms of the mean and the median values and the standard deviation as compared to the original data. If you look at MRI Fusion, really that error bar has just been really narrowed, and so we have a higher resolution product with way less error. That's really going to be useful for you to get the information from the data at a higher resolution. So this is some work that Wolfgang has presented at conferences, and I encourage you to look up that paper or contact us if you'd like us to send it to you. Another key piece of technology that's been added in our stack is basically the ability to do spectral classification right off the data. So part of Jason's demo is going to be basically ingesting a Landsat image and then showing you that spectral classification that's been performed, that's going to allow you allows us to leverage those layers for further processing down the chain as we go. These are some examples of the spec class, which is the name of our algorithm as compared to La Source, and you can see some of the differences here. And again, this is part of Wolfgang's work. He presented this at Pecora in 2019, and you know, there's pros and cons of each one, but you know, the idea here is to generate those information layers so that they can be used for getting to a higher quality ARD product through the production chain. And so this spectral classification that occurs when we ingest the data is a critical piece of technology that's been added to improve the quality of the ARD products. Here we just have just an animation of that same data set, and I just wanted to give everyone a taste for you know, why you would do this and why it's important. And you can see some of the information that can actually be teased out of the data. You can see a construction startup area down in the bottom left portion of this data set. This is just over like a 4-month period, and this area here is actually a staging area. What happens is vehicles are shipped into Los Angeles port. They're carried by train into this staging area. They're loaded onto trucks, and then those trucks then travel throughout the US and into other parts of North America to distribute those vehicles into car dealerships and so on. So, you know, having this temporal element of the data can help you understand what's happening on the ground. So you can measure housing startups, you can measure activity levels as it relates to industrial activity. In this case, you know, how many cars are being built, how many cars are being shipped. You know, we can get a sense, we can develop information layers that have that temporal element as a result of this work that's being done. And there'll be more examples coming up. Just a couple more words on Card4L. So this is a key thing that PCI is supporting. So CIOS, which is the Committee on Earth Observation Satellites. It's an international group, a not-for-profit group that's made up of different satellite operators around the world and people who operate in that sphere. And we certainly participate with CIOS. CIOS has really been key in developing this standard. It's called CARD for L, so CIOS Analysis Ready Data for Land. And there's a website that you can visit where they're actually developing specifications together with the international community so that people can normalize their way that they're generating those data products, and so that collectively, as an international community of Earth observation practitioners and scientists, we can all be working with the same type of data. That's really what's important here, is if we want to aggregate all these pilot projects, you know, we're all doing these interesting projects where we're drilling in through time over these local areas. But if we want to aggregate that globally and be measuring things at a global scale, which is obviously very important as we look at climate change effects, having a normalized, standardized way to correct the data and to take those quantitative measurements is very important. So CIOS has been very important in developing this standard with the international community. And we have been in lockstep with some of these international organizations. This is Arnold Huffam, who's our Vice President of Sales. Arn participates, Wolfgang participates, Guillaume, who's on this call right now, has participated in these international fora where really we are making sure that the standardization of these products is put on the front burner, not the back burner. It's what's going to make it possible for all of us to advance the utilization of this technology. So I'm going to take a quick little break here and go ahead and launch poll number 2. And so poll number 2 is relates to the data sources. So what are your sources of data for temporal analysis? We've listed a few here. Hopefully you recognize them or have thoughts about them. Maybe we've missed some. If we miss some, don't be shy to type something in the questions panel and say, hey, you forgot about this one. But we've got listed there the USGS Landsat ARD data, which is available through Earth Explorer for all of the US for sure, and increasingly globally. ESA is distributing Sentinel ARD data as well as their Centaur algorithm to produce ARD data. Amazon actually hosts some data on their cloud. So they have buckets set up with Landsat 8 data that's available. European Space Agency has different platforms, DIAS, which is there's actually 5 different platforms, Synergize, EOS, just basically platforms where the data is been normalized and is available for analysis. And then non-ARD data. So maybe in your country, there's a ground station that has spot data or rapid eye data, other types of data, high resolution data, and you know there isn't really a source for that ARD data available, and that's kind of what you're working with. So I'm going to close that down in a few seconds here, and kind of interesting to see the results. So a lot of you using USGS and ESA, which is a wonderful source of data, as I mentioned, because it is open source. But it looks like quite a few of you are using non-ARD data or data sets that are not sort of easily distributable. And if you have another source of data, or if we've missed a category, we'd love to hear from you in the questions panel. So at this point, I'm going to take a little break, have a drink of water, and pass over to Jason.
Thanks, Kevin. Hello, everyone. I'm just going to show my screen. Here we go. Perfect. Hello, everyone. Thanks, Kevin, for the amazing introduction. So as Kevin mentioned, I'm just going to quickly cover the number of different GXL jobs and operations we have for ARD processing. So it's important to note that we have developed a number of different operations for ARD processing to be used for the Open Data Cube. So we have we have an array of different tools.
Sorry, Jason.
We're not quite seeing your screen yet,
yeah,
Jason.
we don't see your screen.
You can't see my screen? Okay, strange.
I'm going to make you a presenter.
No, I'm okay.
Oh, sorry about that.
No worries. I'm just going to do that, show my screen. Wonderful.
Perfect.
Sorry about that, everyone. Everyone can see it now?
We're good.
Perfect. Okay. So just a brief introduction of what is the GXL. Kevin's made some mentions of this enterprise tool. Just to give a really brief overview, it's just made up of a number of different components, a web interface as we see in front. It's also combined with a controller, a data server, a processing server, to be used for high volume and scalable processing. So I'm just going to sign in, and what we see first, as we sign in, is the job list. So in our first window, this is the job monitoring list. As we see here, I've run just a single job for a data ingest. It was completed, just a little notification. So this is where all the jobs we're running or are about to run will be listed. I can select the create job, which provides the list of all available jobs for the GXL system itself. But we also on the left have different collections of workflows. So for instance, the ARD analysis ready data workflow contains all the different jobs used that Kevin made mention of. So the modus preparation, normalization, super registration. So the first job I just want to show you a quick little run of the GXL is the data ingest job. So I'm going to all, and so the importance of the data ingest job, which begins most of all of our workflows, is that this tool iteratively search through a folder or a drive to identify all Earth observation images for the processing. And this can be done for one image, or it can go in just 1,000 images. It's quite powerful. It also can generate a ground control point tie point exclusion mask utilizing that spectral classification tool Kevin showed previously. So what I'm going to do, it's really quick, I'm just going to use ingest one image just to get the point across. So I'm just going to point to this folder that has one Landsat image I downloaded from USGS. I'm going to point to the input scenes just to showcase how the GXL is used. Provide an output location. So I'm just going to call it output 1. I'm going to how to build pyramids, create the exclusion mask, and going to give it a comment. Let's call this webinar live. Live. So I'm going to submit the job, and as we see, we now have the job status. It's ready. It's now running, and at the bottom of the log, it's going to be detailing how the process is running. So we have 2 child jobs related. So it is ingesting the panchromatic and the multispectral at the same time. And once those are completed, it will then generate the spectral classification. Now, as that's running, I'll come back to it in a second. I'm going to go up to the create job window and go to the analysis ready data. So the first job that Kevin made mention of was that super registration job, which of course the user can utilize a folder of orthos that they have ortho-rectified using our workflow, or they could have downloaded, for instance, from the USGS or any other data provider. So they can point to the ortho images, provided a reference image, provided a number of different parameters for collecting ground control points. Now, the important thing of why we suggest using the data ingest tool is because this will actually make use of that exclusion mask area to make sure that it does not collect ground control points on areas such as water or clouds, just to make sure that we are improving the best as we can. So once the super registration job has been completed, we can go back. We can then perform the modus preparation job as well, which the user will input their super registered images. And of course, because we're making a modus composite, we can collect modus images before and after the target image that's being processed. So this system will automatically go online and download all the associated modus images to generate the composite, which then will be used for the spectral normalization to modus job. Once that has been completed and your imagery has now been radiometrically calibrated or normalized based on the MODIS images and MODIS composites, all we need to do is go to the select the pan sharpening job and choose, provided the panchromatic folder, the multispectral images, and of course choose the MRI Fusion. So now that I've shown you a few of the jobs and just how the GXL looks and the number of different parameters and the ARD jobs, let's go look at our previous job. So it's completed. So I'm going to choose the webinar live. So it's ingested all the images, it's created the exclusion mask, and it just says no raw. The only warning was that the imagery was not raw, so it didn't create an ortho engine project that we would use if we needed to collect ground control points and then perform the ortho rectification. Just because these have already been ortho rectified, that's the only warning. That's the reason it's providing that warning message. So it's always good with the log. It always helps figure out why, and just to notify you. So I'm going to go to the output one folder. So we have our multispectral file. I'm going to quickly open it up. Just a simple Landsat image over Toronto. And of course the GTA, the Greater Toronto Area. We can see there's a number of different land cover classes, water, cloud. So let's see how the spectral pre-classification ran. So I'm just going to take it and drag and drop into the focus window. And we can see, I'm going to zoom out. I'm going to open up the table, and we can see that cloud's been identified, water, urban areas, and agricultural zones. So all this is really useful for, of course, the exclusion mask, but even for initial analysis of your data. So there's a number of amazing tools that GXL and Geomatica has for the ARD processing and workflow.
Great. Thanks for that demo, Jason. Hopefully that gives everyone a sense. And as I mentioned, or as Jason mentioned, I guess we're primarily showing for one image there, just in the interest of time, but you could obviously work your way through quite a bit of data. All right, so it looks like the right screen is up and everything's fine. Good to go, Mauro? Everything fine? Just want a green light from you.
Yep, everything's good.
Okay, great, thanks. Okay, so if we just I've just got a little bit of wrap up to do, I guess, or just getting into the other two pillars now. So the second pillar that we talked about in terms of temporal analysis is really that open data cube piece. And this is a piece of technology, again, that actually was born out of Geoscience Australia. And sorry, if I can get you guys to mute your lines if you're not talking. That'd be great, thanks. So the open data cube came out of Geoscience Australia, and it's been adopted by CIOS, that same body that I talked about, the international body that I talked about earlier, and the code has been open source. And what that means is you can basically build a four-dimensional analysis framework. So there's a framework to allow you to store all of your data and traverse those image stacks. And really, that's great for large volumes of data, for doing that temporal analysis. You can, either take a thin slice or a deep slice. You can, take a big piece, a small piece. You get all of your data into the data cube, and then you can basically start to explore it and discover what information is available inside your data stack. We love the fact that there's different versions of the Open Data Cube, and I'll get to that in a minute. But there's a continuous change detection algorithm that we've leveraged for the case study with Environment Canada that is Python based, and so that really allows us to integrate our custom workflow together with the Open Data Cube and the continuous change detection. This is one of the earliest examples that we did, where we basically took multi-temporal Sentinel-2 data over an area in Alberta, Canada, and we were able to detect over about a 2-year period some deforestation activity related to the oil sands production near Fort McMurray, Alberta. So it gives you an idea of the information that's hidden in the data. Yes, we can all pull one image up, pull another image up, do some change detection. but really, the fact that the data is available and the fact that we can put it together into these temporal data stacks allows us to explore and discover information that we might not otherwise see. There's some other ways that this can be brought forward. So the one that I just showed was more of a graphical user interface version of the Open Data Cube, but there's also a Jupyter Notebook available. And here, if you go to the Open Data Cube Git repository, you can see that there's the UI version, which is the one I just showed you. There's also a Jupyter Notebook, which we've used ourselves, and I'll show you an example of a Jupyter Notebook that we built for one of our clients. And then there's just straight up Python versions of the Data Cube as well, which you can use. But this is just showing you an actual Data Cube that we have put together for one of our clients. And in this case, they're looking at creating a deep temporal stack of spot data. And so we were able to not only create all of the analysis ready data from the raw level 1 data, but we're also able to export it in such a way that it can be read into the Data Cube, ingested into the Data Cube. So we have methods for doing that as well. And then basically what you can do from there is you can implement, different algorithms. So this particular algorithm here is extract cloud-free clear spot observations from sensors. And you can see the code snippet there, and you can play with the different bands. You can tweak some of the parameters, you hit enter, and then it runs that algorithm in the Data Cube, and it shows you the results at the bottom through the Jupyter Notebook interface. So if that's a way that you would like to work, that's an interesting way to leverage the Data Cube architecture. Just to give you another sort of taste for what's possible, why you would want to do this. This is one of the algorithms that is available through the Data Cube. It's called Water Observation from Space, and basically it's an open source algorithm that can traverse through that temporal stack and understand the extent of the water over time. And here we have two simple maps. One is the highest tidal extent and one is the lowest tidal extent. And we're able to generate that map over this geography because the data has all been stacked nicely. So that's one of the algorithms that could be run on the Open Data Cube. You can, of course, write your own algorithms and bring them to your instance of the Data Cube. We've actually used that algorithm for one of our customers. And so what you see here is actually an animation of a reservoir that's just north of a large city. And so monitoring the extent of this reservoir in terms of how much water is contained in it can absolutely inform policy or help policymakers make decisions about reducing water usage to water people's lawns or irrigate fields or even water consumption in general. So there's really interesting data here over this particular location. So the third thing I want to talk about is the multi-temporal analysis. And I'm going to go really quickly over all the steps that we use, which might be a little bit repetitive, but I think it's good to give you a sense of how we're able to take a project from beginning to end to get to that answer as to why you would want to do temporal and multi-temporal analysis and how you can benefit from it. So we've been working with Environment and Climate Change Canada. You can see this is one of the reports that's been authored. This is a regular report that is authored by our government, our Canadian government, and we work with some colleagues who are directly responsible for the science and the methodology to create the data that goes into these reports. So it's the Pollutant Inventories and Reporting Division, and they really see Earth observation as a promising technology that can be leveraged to help them achieve their goals. So they're interested to quantifiably measure the land use change using multi-temporal analysis. And so what we did is we actually worked over the city of Toronto to understand the rates of urbanization and the transformation of the land from the different classes over time. You know, the classic scenario is you have a forested plot that gets harvested. Maybe that gets converted to agriculture, and then from there eventually it gets converted to commercial or residential land. And so understanding where those changes are occurring and how that might contribute to the carbon budget within Canada is a piece of information that this particular group is interested in leveraging for the benefit of getting more accurate measurements. This is the study area. So we looked, you can see the city of Toronto in the red area down below there. So it actually means that we have to go get four different Landsat images to cover the entire area. We worked on a subset of this area, so you can see that over the 30-year period from '89 to 2019, you can see the distribution of the data collections over time. Of course, we're dealing with clouds and so on, but we've got about 600 images in this one particular location that we worked on. And we leverage the technology that's available to work our way through the entire ARD production chain to get to that end bar product at the bottom. So either using the ARD products available for USGS or generating the data from scratch using level 1, both are possible. And we did do a little bit of both with this project. And then the next thing that we did is we actually we asked Environment Canada to classify the images on an object basis. So rather than doing a per pixel classification, we actually use some of the technology that we have, which is segmentation. And we created objects, and then we asked Environment Canada to basically classify those objects and generate a land cover classification according to these 6 classes. So it's a very simple case. It's not exhaustive by any means, but it is a way to understand some of the key land transformations that are of interest for Environment Canada. So I mentioned forest, I mentioned agriculture, I mentioned commercial, residential. So these are all transformations in these classes are going to be useful from a scientific basis to understand carbon increases or decreases and how that contributes overall to Canada's picture in terms of land use and land cover. So this classification was generated by Environment Canada. And then what we did is we used this algorithm from Dr. Zhu, who's a researcher based currently at the University of Connecticut. And he's really innovated this technique, which is called Continuous Change Detection and Classification, CCDC. If you're not familiar with it, I encourage you to go read the papers. It's a very, very novel technique, and you can see this technique here applied. And what I've decided to show you first is some areas that have not changed. And so the green dots, all those green crosshairs are measurements. Those are quantitative measurements that have been normalized radiometrically and geometrically. And this particular object that's highlighted, so the yellow objects that are highlighted, so this one's a grass parcel near an airport that hasn't changed in 30 years. And it has a particular pattern. It kind of goes a little bit down, probably that's the winter time in terms of its reflectance, and then it goes up a little bit in the summer, and it kind of cycles up and down, up and down, up and down, up and down. And so it develops this kind of harmonic pattern or this repeated pattern. And there's never really a break. And so what the continuous change detection algorithm seeks to do is to statistically detect where that break has occurred if there is a change in the land. And you can see the same algorithm applied to a polygon on the bottom, which is a forested polygon. This is an urban forest just in Richmond Hill, just close to our offices actually. And this has been here for quite a number of years as well, and there really isn't any difference in the pattern. Now, if we take these two harmonic patterns, you can see that the level of reflectance is different depending on the land cover, obviously the grass versus forest. And then you look in an area that has changed. So basically this area has been developed into a residential area. And you can see that there's a break. So this line here detects a break in the pattern very early on. And then we have this residential pattern that kind of repeats over a number of years. And then there's another break further on where there's a change in the pattern again. So what this can do is it can tell policymakers such as Environment Canada from which class to which class, and when did that occur, and how big is the area. And that can be put into models to understand the effect of that land conversion from the different classes in terms of carbon storage or carbon emission. So scaling up is very important. This is kind of working towards next steps. So you can see that we worked on a sort of a very small area within Ontario in Toronto, but these are all the census municipal areas or the big urban areas in Canada. And the dark areas that are highlighted there are basically all of the other Landsat images that would have to be obtained in order to grow this or to expand this analysis across the whole country. So quite a bit of data. I think there's roughly 100 frames or so, if I remember correctly. And each one of those frames, you know, has a 30-year span. So it's a big data set, and it's important to have the right infrastructure and the right automation to be able to pull all of this data up at the scale to be able to repeat this analysis on an iterative basis across a much larger area to get that Canada-wide picture. And this could also be reported, or sorry, this could also be repeated for deforestation or for agriculture or for wetlands. You know, different government agencies might have a slightly different lens. I'm thinking of an Agriculture and Agri-Food Canada or National Wildlife Research Center in Canada, and maybe similar organizations within your countries that have a different mandate as it relates to monitoring change over land. So future work that we're developing with Environment Canada includes potentially including RadarSat constellation missions. So radar data is something we haven't talked about, but it's definitely something that we are working on in terms of bringing that type of data. Scaling the solution, of course, to work at a national scale. So Environment Canada has actually been using some of our GXL technology to look at how they could scale that up. And more of the science. So there's the last bullet here is the carbon biomass estimates for the conversion of land use classes. So there's work happening right now with high resolution data and scientists and graduate students at the University of Waterloo and in other universities in Canada to try to make that link between that sort of medium resolution data, the Landsat and Sentinel data, down to you know, individual tree counts or composition of those objects. You know, what are they composed of over time, to establish that relationship and get an even better estimate of that biomass change. So I can show you the live map, but while I do that, I'm going to open up for questions, and I'm going to lean on Jason and Mauro to handle the questions a little bit while I get myself organized here. Can you guys maybe move over to that?
Yeah, we've got Jason right now answering questions via the questions panel. I think Guillaume is also on the line answering some questions.
Sure. Guillaume can also talk. He can come in as well.
Yeah. Oh, just before we do that, I forgot one more thing. So there's a last poll that we haven't done yet, and then we'll kind of wrap up. So the question is, what software are you currently using to do multi-temporal analysis? So maybe you're using Google Earth Engine, maybe you're just using open source libraries, maybe it's a mix of open source, commercial software, in-house, and maybe your work is really centered around the statistical analysis like MATLAB, R, and so on. These are not mutually exclusive. You can answer all of them. You know, we're just interested to see what people are using, and also interested to hear about what's working, what isn't working, and as people get exposed to what we're offering, we obviously love to hear more about how we can improve our technology. I'm going to leave that open a little bit longer. And close that down. So I'll just share that out so everyone can see. So quite a few people doing a mix, it looks like. Open source, commercial software, in-house. Google Earth Engine, definitely a lot of use there as well, open source. And so kind of a nice spread. People are using a lot of different things, which is great. I think if we're going to really make an impact as an industry, we need to develop all of our technology and make it available. So yeah, guys, any questions you want to throw Guillaume's way?
Yeah. Quick thing, we're going through the questions. One new question just came in. It's just about the training set that was used. And yes, a training set has to be developed and designed or defined. That's going to be used to classify all the segments or the statistics from the segments that are collected.
Yeah, and
Sorry,
to elaborate on that, I was going to say, in the case of Environment Canada, they did provide the training sites. We were involved in the making, but they were really the one that created the training sites using different techniques. You can use whatever. You can use a classification layer that you already have, or you can use ground truth. It's really up to you at that point. The only requirement of the CCD algorithm or CCDC is to have a good spectral distribution. Make sure that when you classify something, you have a good bit of everything. You know, if you have agriculture, you want to make sure you have all the kind of crops, and same thing for the forest and that kind of thing.
Great.
And can I say something? So
you're there, Wolfgang. Welcome.
So you can use any kind of classifiers. We used random forest classifier, I think, Guillaume, if I'm correct. But yes. You could also use things like deep neural nets, TensorFlow, etc., to then classify the coefficients, basically, that CCD algorithm provides for each object.
Okay, we have a question that has been answered as it relates to ARD masks. Wolfgang, maybe you can take this one. Does ARD masks produce shadows?
Yeah, so I couldn't answer these questions myself, so I sent them off to Jason and he pasted them in. Yes, so ARD produces shadow masks. The first implementation that we had didn't do as good a job because it didn't make use of contextual information. So there's going to be a shadow close to a cloud at a certain distance from at a certain angle, etc. That's the contextual information. But we have since updated that, and we have improved our shadow masks substantially. So what is currently released in the software, those shadow masks aren't that great yet. But very soon we're going to release one that produces a much better result. Hopefully a lot better than what the USGS and ESA are providing for their data. And
great, perfect. Got a question here which is kind of interesting. Someone's asking, is there a minimum size in terms of the number of images? You know, maybe what's coming across is this is all a lot of work to you know, where does it start to make sense in terms of how deep of a stack to actually look at you leveraging DataCube technology? Maybe Wolfgang or Guillaume, you guys can weigh in terms of your opinion there.
Yeah, actually, I was typing the answer while you were reading it. So I'll repeat what I said, which is, yeah, I mean, 20 images is a bit kind of a small side of things for an open data cube. You could probably get away with simpler tools to use. What I will say, though, is that bringing your data to an ARD level is definitely a must. I mean, that's going to make your analysis so much more accurate. You reduce your error. That you can see even with 2 images. So 20 is definitely would be important. What I would add on the ODC is 2 things. First, you have a lot of already made algorithm, and you can explore your data with them. So that's a reason for going at it. Another one is, you know, maybe your study area is 20 images, but if you want to generalize your research on a bigger data set, a deeper stack, if you kind of develop within the ODC framework, you can definitely do that from the get-go, right? You simply push a button and then you can run your algorithm on the entire Landsat archive if you want.
Okay.
Yeah, so I would just say it really depends on the application. If you've got a monitoring application somewhere in the desert or in a city, a stack of 20 data sets or images or 30 images might be sufficient. If you're monitoring change on an agricultural field, then you would want a lot of observations in that season. And if you want to do forest change detection, etc., you would want, you know, an archive of Landsat over that area. And especially if you're after very small changes that you would like to identify and map, you would need a deep stack of data.
Okay, question here about, I guess it's a product question, so maybe Guillaume or myself can take it. Does GXL Banff include tools for image segmentation, deep learning algorithms for processing high resolution satellite imagery? So I guess I can take a stab at it. Guillaume, you can fill in the blanks. So GXL basically is part of our platform. The technology that we developed can be brought across our platform. So we have Geomatica algorithms, we have GXL, which is an enterprise framework. So we can customize the GXL, we can pull through the algorithms. So segmentation for sure. If it's not there, we can add it in. Deep learning, not quite there with the deep learning as far as I understand, but we are developing technology around that. And I think a lot of this work that we're doing around ARD is going to make deep learning possible or easier. Again, getting to those quantitative measurements and reducing the noise in the data, that's going to be really important. Not sure if Wolfgang or Guillaume, if you guys want to add anything on that.
Yeah, so if I can say something, so our system is open, the GXL is an open system, and it allows you to incorporate third-party libraries. So if you want to integrate TensorFlow in there, you can do that, and build your own workflows. So we don't want to be the best in everything. So deep learning is a field that we have not spent a lot of effort on there because we don't have the leading expertise. I think Google has got much deeper pockets than we have. So we rely on the work that is done by the community, and then make it easy for our users to integrate that technology into our own.
Right. Okay. Is there any other questions jumping out of you guys that you want to pick up? Or there's one question here that's interesting. How do you normalize radiometric resolutions between Landsat 8 and Landsat 7? I guess the bands, the difference in the bands or slight differences in the radiometry from sensor to sensor?
Yes. So obviously there are differences between all the sensors, and if you want to do a multi-sensor analysis, you need to match everything to a golden standard, so to say. So we are able to model the spectral response functions and the spatial distribution functions, etc., that are required, so that the signal can be transposed from one dimension to the next. So we match everything to a golden standard, which is in the modus MCD43, so that you can do analysis across sensors.
Perfect. I think I'm going to leave it there. Those are really great questions. I want to thank everyone for asking those. I'm just going to show my screen again. Oops. Yeah, so just kind of wrapping up here. Whoops, wrong screen. Sorry about that. Yeah. So basically, some resources for you to go check out. We've got our support landing page, which is obviously got a lot of case studies and tutorials and so on. We actually have a developer zone where if you want to use our algorithms and connect them to other things. As Wolfgang mentioned, our system is open through Python. You can bolt on other things to it, and we've certainly done that ourselves. And then there's some other courses available. So these are self-driven courses that you can participate in as well on Udemy. YouTube channel, lots of resources there as well. A recorded version of this webinar is going to be available. So we really encourage you to reach out. We're all pretty much the last name at PCI Geomatics. So I'm Jones at PCI Geomatics. Wolfgang is L-U-C-K. Guillaume is Morin, M-O-R-N, and so on. So all of us are available. We would love to hear from you if you have any further questions about this. We really want to thank you for attending this webinar. It's great to have you, and if you have any questions, please get in touch. I'd like to thank Wolfgang and Guillaume, obviously, for this wonderful project, and also for Jason to present it to us, and our collaborators from Environment Canada have been really important as well to get us to this point with this technology. So looking forward to hearing from you.
I'd like to say thank you to you too, Kevin, for the awesome presentation.
Great. All right, thanks everyone.